All right, here we are in assignment 10. Questions 2 through 6 have this group, these three groups of equations. And so when we do this assignment, I'll often refer back to, say, group 2, equation 3, or group 3, equation 2, and so on, and you'll know what I'm talking about. These equations are also found on your equation sheet. Okay, here we are at problem 8, and most of the problems involve this type of apparatus where we have a disc on a rotating base and a string wrapped around the hub of the base attached to a hanging mass. So this mass puts a tension in the string and it causes the disc to rotate as the string unwinds from the base. So this is what we would use in lab if we were actually in lab. And so it's important to understand that this is a pretty massive, large object, and it's going to make this mass fall very slowly. If we just drop the mass, it would hit the ground and the floor in less than a half a second, but here it's going to take 5 to 10 seconds to reach the floor as this thing rotates. But as it falls, the mass is going to accelerate, and the disc is going to spin faster and faster and faster, and it's also going to accelerate. And they're tied together by this string. So let's begin the problem. The first question is average acceleration. So go to group 1, equation 2, and you'll see that the average acceleration, actually let me pause. Actually, what I want to say is pause the video, take that group 1 equation 2 and see if you can get the answer to the first blank space. Pause the video and do that. Okay, this is what you should have done. You should have written down the equation. Delta theta means theta final minus theta initial. T finus minus t initial. T initial is usually 0, so we usually just write this as t. So the angular displacement, the amount it went, was 3 rotations, 5.94 seconds. We get 0.505 rotations per second, a little less than a half a rotation per second. But oops, if we look at the box, it wants the answer in radians per second. So this is the correct answer, but the wrong units. So let's change the rotations to radians. So 3 rotations, we multiply by 2 pi radians divided by 1 rotation. The rotations cancel. You see we'll always be multiplying by 2 pi the rotation. So that's 6 pi radians. Each circle is 2 pi. There's 3 of them, so it's 6 pi. And 6 pi is a number. Multiplying it out would be 18.85 radians. We often just leave it as 6 pi and then put pi in the calculator. So now I'm going to take my equation down here, and I've got my 6 pi radians divided by 5.94. This is the number I get. I'm going to keep this number because I need to use this later on when we do calculations. But in the box, you're going to type 3.17 because it rounds down to 7. Okay, let's continue. So the next question is how many significant figures in your answer? You want to write a 3 in there. Why is that? Because this is 3, this is 3. All the numbers given excuse me, are 3 significant figures, and so that's what our answer should be. But notice we're saving the extra digit so that we don't get calculations to avoid rounding errors. You see this? You'll see what I mean in a minute. Okay, so the next question is, what is the initial angular velocity? Okay, that's just a matter of recognizing what we're doing. We're releasing it from rest. It says so in the problem somewhere. So that's 0. What's the final? Okay, so to get the final, we want to use equation, which one? Take a look at your list. Okay, this one's a little tricky. You got to go back to group 2, and if you look at equation 2, you'll see it in this form. Well, inside of here is what we need. Omega, notice if I take this part and I take the t out, right? I divide both sides by t. I have that omega average is omega final plus omega initial divided by 2. So that's the equation you want to use to get omega final. Try using that equation and see if you can get the answer. Pause the video and do that. Okay, I hope you get this. So let's look at what I did. I brought the equation here, and I did the algebra. I want omega final. So I multiply 2 to both sides. I bring this over here and I turn it around. Omega final is 2 times omega average minus omega initial. But omega initial is 0. So omega final is simply 2 times this number. I get this number and it rounds to 6.35. Now notice, if you had used the 3.17 that we put in the box, you would have gotten 6.34, and you'd get the wrong answer. That would be a rounding error. So this is the number that goes in the next box. Okay, so you're putting the 0 here, we're putting the 6.35 here, and now we want to get the angular acceleration. So go to your equation, see if you can find the equation, and then try calculating that. Pause the video. Go ahead, give it a try. Okay, how did you do? This is this equation is group 1, number 4, and that's the easiest one to use. This is group 2, number 1. But if you look at these, they're algebraically, they're identical. So you could start with this and solve for alpha, or you can just use this. This is the one I took, group 1, equation 4. And so that's omega final minus omega initial over the time. We have our omega final. Notice I put the whole number in there. Omega initial 0, that's the time. I get this. So it rounds out to this. This is the number that will go in the box, but I'm going to save this number. And the important thing to realize is that the one thing that's constant throughout this problem is the acceleration. So this is a number that we want to save. We're going to use it for later parts of the problem. Okay, 3 more parts. Let's see if we can do these all at once. So next part is, what's the angular velocity at 4 seconds? So that's going to be less than, right, omega final here. So if this takes about 6 seconds, this is 4 seconds, this, we could guess this omega is going to be about 4, because it's going from 0 to 6, right? Just look at the numbers. And what is the angular velocity after 2 rotations? So that's 2/3 of the 3 rotations, but remember it's accelerating, so it's going slow through the, it's going to go fast in the last rotation. So you might be surprised at the answer to this. So that's that. And then we want to get, how long does it take the disk to go through the first 2 rotations? In other words, it takes 5.94 seconds to do 3. How long is it going to take to do 2? So go ahead and try to do as much of that as you can. Pause the video and then come back. Okay, continuing. So here's the 3 steps to the remaining solution. See how you did. So in the first one, we take this equation 1 from group 2. We're looking for omega final. We have the acceleration, that's constant. Only in this case, we're going 4 seconds rather than the 5.94. So we simply use this equation. And the acceleration times the 4 seconds gives us what we said we expected. We expected after 4 seconds it would be a little bit more than 4 radians per second. Okay, now we want to find in the next box, you're asked to find omega final for 2 rotations, so you don't have the time. So if you go to your equations, you'll see in group 2, equation 4 has no time in it. This is the equation we often use when there's no time. So I wrote the equation down. Omega initial is 0. It starts from rest. So omega final is the square root of what remains. So omega final is the square root of 2 times alpha times delta theta. Delta theta is 2 rotations, so 2 times 2 pi will give us the rotations in radians. And then when we do all that and take the square root, this is what we get. Okay, now we know omega final, so now we can figure out how long it takes to get there. So we go back to equation 1 from group 2. No, actually, whoops, equation 3. Go to group 2, equation 3. And we're talking about 2 rotations. We know this is 0. We know what the acceleration is. So because that's 0, we solve for time. You can do the algebra and you get time equals 2 times the 2 rotations in radians divided by the acceleration. There it is, 2 times the 2 times 2 pi radians. That's the 2 rotations in radians divided by the acceleration. Gives you the final time of 4.85 seconds. So good, we're done with that one. Okay, before we close, let me scroll. Here's number 8. Let's scroll through the rest of the assignment. So here's a similar one. The one thing you might run into here is when you get to the end of this, it asks you how long will it take to go through the disk to go through the first 5 rotations. Let me just, yeah, so this is 5 rotations. So how long will it take to do the 5 rotations? Oh no, I'm misreading it. How long will it take to go through the first of the 5 rotations? That's easy because that's starting from 0. But if you want to know how long it takes to go through the last of the 5 rotations, you're not starting from 0. So you have to find out the time it takes to go through 4 rotations and subtract it from the time it takes to go through 5 rotations. That's one that people often have trouble with. Continuing, whoops, let me go back here, pause. Okay, so we're going to scroll through number 10, 11, 12, those are single answers. I'll let you do those. I don't think there's anything unusual in there. And then when you finish with these, you'll come to a different apparatus. So with this one, you want to notice that there's like a hoop on a turntable. So the string is wrapped around the hub as usual. There's a pulley. This is all related through this. But there's a skirt sticking out. This is sticking out past the edge of the hoop. And it's horizontal. And so the photo gate, this strip is going to go through and block the photo gate like we did in lab. And so the diameter of this is 22. The radius then is 11, but this sticks out an extra centimeter, so that's going to be 12 centimeters. People often get confused about that, so just be clear about that. And the other part that I forgot to mention was that as this thing spins, this is falling, and so they're connected through the string which is wrapped around the hub. And so whenever you have to go from, like, say, we know the acceleration of this, the angle acceleration, how is that related to the linear acceleration of this? So whenever you go from angular to linear quantities, you got to use those equations from group 3. Right? So these equations in group 3, let me just expand that. These equations from group 3 are the ones you're going to use, and they have numbers like the rest of them. So if you're trying to get a distance when you have the angle, you use this equation. If you're trying to get a linear velocity, you use this equation, and it's always related to the radius. So if you wanted to know the speed of the mass falling compared to the spinning rate of the disk, you would use the radius of the hub, because the string is wrapped around the hub, and so that's the place the hub is spinning around at the same speed as the falling mass. In the same way, if you want to get the acceleration of the falling mass, you use the angular acceleration of the disk times the radius of the hub. So just remember that when those kinds of questions come up.